Hello everyone, this is a short presentation video for our work Enhancing Cost Efficiency in Active Learning with Candidate Security, accepted at TMLR. Our paper introduces a cost-efficient active learning framework for classification. I'm Yeho Kwon, and this is joint work with Seon Hwang, Hoyoung Kim, Jung-Soo Ok, and Suak Kwak. Active learning improves labeling efficiency by repeatedly selecting samples for annotation and retraining the model. The loop begins with an initial labeled dataset. A model is trained, then an acquisition function based on the model's predictions chooses which unlabeled samples to query. These samples are annotated and added back into the training set. But where does the main cost arise? It's in annotation. Each time the oracle provides a label, it requires effort and time. That's why it's important not only to select informative samples, but also to consider annotation cost. Our approach addresses this by proposing a more efficient query design for retrieving labels and a cost-efficient sampling method for choosing which samples to annotate. Consider labeling a picture of a dog. If there are 100 possible classes, the annotator must search through all 100. The effort grows with the number of options and becomes especially burdensome if the label involves unfamiliar terms, such as medical terminology. To cut annotation cost, we leverage the trained model to filter out unlikely labels and present only the most plausible ones. For example, for a Maltese dog, the options might be lion, king penguin, Maltese dog, Labrador retriever, and tiger cat. We name this the candidate security. The idea is straightforward: reduce cost by narrowing down class options. We first define annotation cost of choosing one label among L options. A 2020 NeurIPS paper modeled this cost as log base 2 of L. For instance, selecting from 5 class options incurs a cost of log base 2 of 5. To verify this model, we conducted a user study where annotators selected the correct class given 4, 8, 16, or 32 options. The actual annotation time correlated with the theoretical cost with a coefficient of 0.97, confirming that the model closely reflects real annotation time. The figure on the left side is an example used in the user study. Following this cost model, we define the cost of candidate security. For an input and its candidate set, 2 cases occur. If the candidate set includes the ground truth label, the cost is log base 2 of k plus 1, where k is the set size, with the plus 1 accounting for the none of the above option. If the ground truth label is absent, a follow-up query with the remaining labels incurs an additional cost of log base 2 of L minus k. This suggests candidate sets should be small, yet reliably include the ground truth to reduce cost. So CSQ is basically composed of 2 questions. Select the ground truth class from the candidate set, or choose none of the above. Only if none of the above is chosen, select the ground truth from the L minus k many remaining classes. To construct candidate sets, we employ conformal prediction. Unlike a single prediction, conformal prediction produces a set of predictions sized according to the model's confidence. In other words, conformal prediction is a mathematical tool for constructing a set of predictions to include the ground truth class, where each set is properly sized based on the certainty of the model about the input. For easy samples, the set is small. For harder ones, it expands. As can be seen in the figures, the model produces different conformal sets, though the 2 images share the same ground truth. This ensures flexibility, dynamically adjusting as the model improves through successive active learning rounds. It also comes with a theoretical guarantee to include the ground truth label, which we will discuss later. Here's how candidate sets are constructed. First, we collect a labeled calibration set. We randomly select about 8% of actively sampled data for this purpose. Using model predictions, we compute conformal scores defined as 1 minus the predicted probability of the ground truth label. From these scores, we obtain the empirical quantile Q hat of alpha. Finally, the candidate set is defined as all labels whose predicted probability is at least 1 minus Q hat of alpha. This marginal guarantees ground truth inclusion with probability of 1 minus alpha. Here, the probability term represents the probability that candidate set includes the GT label. The challenge is selecting alpha, which is a hyperparameter. A smaller alpha increases candidate set size, while a larger one risks excluding the ground truth. We resolve this by optimizing alpha to minimize annotation cost on the calibration set. This is achievable because all samples in the calibration set are associated with labels. In practice, this optimization is implemented with a simple grid search, yet it significantly reduces costs compared to manually chosen values. In addition to the query design, we propose a cost-efficient sampling method compatible with existing acquisition functions. Consider two scenarios: one expensive sample versus several cheaper ones. Sometimes multiple cheaper samples are more beneficial. Thus, acquisition functions should account for annotation cost. Our solution is an acquisition function that measures information gain per unit cost. The numerator comes from traditional functions such as entropy or batch, while the denominator is the estimated annotation cost of the sample. Here, D is for balancing informativeness and estimated annotation cost. To validate our framework, we conducted experiments on Cypher 10, Cypher 100, and ImageNet 64x64. We evaluated both annotation cost and model accuracy, comparing our method with conventional query strategies showing all classes, combined with acquisition functions like random, entropy, batch, prop cover, and sol. We also provide additional experiments in the appendix of our paper. First, comparing CSQ combined with cost-efficient sampling to conventional baselines, we see consistent improvements in cost efficiency across all datasets and sampling methods. Specifically, CSQ saves annotation costs by up to 57 percent point on Cypher 10, 45 percent point on Cypher 100, and 44 percent point on ImageNet 64x64. In ablation studies, we compared four settings: CQ, CSQ with a fixed alpha of 0.1, CSQ with our cost-optimized alpha, and CSQ with cost-efficient sampling. When we compare the first two, it's shown that even applying CSQ alone significantly reduces cost. Optimizing alpha further improves efficiency, and our final method, CSQ with cost-efficient entropy sampling, achieves the best performance. So each component contributes to the cost efficiency. For qualitative results, we see that candidate sets adapt to sample difficulty. Easy images on the left side yield small sets, while difficult images on the right side produce larger ones. For instance, two images of a water buffalo may result in different set sizes depending on how hard they are to classify, even though they share the same ground truth label. In summary, we propose candidate set query, an active learning framework that effectively reduces labeling cost by presenting annotators with smaller, reliable sets of candidate labels. We also introduce a cost-efficient acquisition function that balances informativeness and annotation cost. Experiments on multiple datasets demonstrate significant gains in cost efficiency. You can also find our paper on arXiv the source code on GitHub and details on the project page. If you have any questions, please feel free to contact us. Thank you.